In context, we're working through separation of variables in spherical coordinates for the time-independent Schrodinger equation in 3 dimensions. Our overall Schrodinger equation looks like this, and if we make the substitution that psi is equal to r, some unknown function of r, times y, some function of theta and phi, we get these two main pieces. The separation constant that works we call the energy, as before, and the angular part here, we can again apply separation of variables to this, y of theta and phi being expressed as some function capital theta of theta times some function capital phi of phi. And that gave rise to our YLM of theta and phi, our spherical harmonics. The radial part we put off, so let's see what that looks like. What does the radial equation get us? The equation that we're working with here has partial derivatives of r, it has r squareds, it has potentials, which here we're assuming are only functions of radius, since that's getting into the context of the hydrogen atom, which is our goal. And it has these l's, which we got from our separation of variables in the angular part. So we have some constants to work with, and this is the equation that we're going to be discussing. We can simplify this equation by rewriting it as in terms of some new function u given by capital R of r divided by, or multiplied by, r. Put another way, the function capital R of r is given by u divided by r. So u is a function of r, and if we make these substitutions in this original equation, the form of the equation simplifies slightly. For instance, I've got terms like the partial derivative of capital R with respect to r. If I write this in terms of u, it's the partial derivative with respect to r of u over r, and this doesn't look like it's getting very much more simple, but you'll see what happens in a moment. Taking the partial derivative of this, I now have two terms, and I can apply the product rule. One, applying the partial derivative to the u and leaving the 1 over r untouched, or alternatively, leaving the u untouched and applying the partial derivative to the r, in which case I get u over r squared with a minus sign. What I'm going to want to do next is figure out what this term looks like, for instance. And this is, well, it's r squared times d capital R dr. But I know what d capital R dr is now. So I'm going to erase that, and I'm going to substitute in this, which is 1 over r du dr minus u over r squared. You can see the r squareds are at least going to cancel out. So that's a plus. And then I still have this partial derivative with respect to r out front that I have to deal with. So if I substitute in there, I'm going to have, simplifying this a little bit, partial derivative with respect to r of r times u, r not times u, times partial derivative of u with respect to r minus u. And now I have a product here as well. If I let the partial derivative act on the r, leaving the du dr untouched, partial derivative of r with respect to r is just unity. So I get the partial derivative of u with respect to r. And if I let the partial derivative act on the du dr, leaving the r untouched, I get r, second derivative of u with respect to r squared. And then the second term here has a minus sign in front of it, but there's only a single term, so I get a minus partial derivative of u with respect to r. And wonder of wonders, my partial derivative of u's with respect to r's cancel out, and I have just a single term left. This is more or less the entire point of making this substitution. We can convert this relatively complicated combined expression with partial derivatives, multiplication, and then repeated partial derivatives into something much more simple. So our overall equation then, at this point, looks like r, second derivative of u, with respect to r, minus 2mr squared over h bar squared times v of r minus e, not close parentheses, times, capital R here is u over r, and that's all equal to l plus 1 u over r, again substituting in u over r for capital R. Looking at the structure of this equation, I have an r here, I have an r squared here, and a u over r, and a u over r. I can simplify this a little bit by multiplying through by 1 over r. I'll get rid of this r. I have then a 1 over r squared after I've multiplied through by r, which will cancel out my r squared. And I'll just have a 1 over r squared, sort of consolidating the r dependence a little bit. What you get after making some simplifications like that, and I'll rearrange the constants as well to get something that looks a little more familiar, we have minus h bar squared over 2m, multiplying through by minus 1 as well, second derivative of u with respect to r squared, plus our potential function minus h bar squared over 2m l plus 1 over r squared, that's our remaining dependence, multiplied by u equals e times u. This should start looking a little bit familiar. We have what looks like a kinetic energy operator, what looks like a potential energy operator, and what looks like the energy. We're sort of back to what we originally started with. This is our radial equation, and it is essentially identical to the one-dimensional Schrodinger equation, with this being our effective potential. We have our actual potential, which is the function of radius, plus this, what's called the centrifugal term. This potential here, if I plot this, the centrifugal term blows up as r goes to 0. Essentially, this makes it hard for the particle to exist near the origin if we have any non-zero value of L here. If L is 0, of course, the centrifugal term disappears, but if L is non-zero, there is effectively a potential that pushes the particle away from the origin. It's called a centrifugal term in analogy with the centrifugal force that you get when you're thinking about classical physics with particles moving in rotating frames of reference. For instance, swinging a ball around on the end of a string, you have to apply tension to that string to keep the ball going in a circle. This potential essentially takes care of the force, effective force, that wants to push the ball away from you as you're swinging it around on the end of a string. But otherwise, this is exactly the same as our one-dimensional time-independent Schrodinger equation. So let's see what happens. As an example, consider the infinite spherical well. Instead of considering the infinite square well, let's do this in spherical coordinates. Our radial equation now, the potential, V of r, and this is the potential, not the effective potential, has a relatively simple form. For particles less than a certain radius from the origin, the potential is 0, and for particles outside the well, the potential is infinity, the same sort of potential structure that we had when we were dealing with the particle in a box in one dimension. So, first of all, don't need orange. First of all, inside the box, our equation looks relatively simple. Minus h bar squared over 2m, second derivative of u with respect to r, plus h bar squared over 2m L plus 1 over r squared. That's our centrifugal term times u is equal to e u. So this is our radial equation for regions inside the box. We can simplify this a little bit if we make the same sort of substitutions that we made when we were working with the one variable particle in a box. Namely, let's define k squared to be equal to 2me over h bar squared, effectively multiplying through by this h bar squared over 2me squared. And what we get when we do that is the second derivative of u with respect to r squared is equal then, rearranging terms, to L plus 1 over r squared minus k squared, our constant which includes the energy, times u. That's the equation we have to work with. And we'll solve that in a minute. Outside, of course, well, v goes to infinity, so that's a problem. Essentially what that means is that our wave function has to be equal to 0. Putting things in terms of this u also has to be 0 outside. On the boundary, the question is what happens to the wave function as it approaches a, or as the radius approaches a. And the same thing happens in this case as has had to happen when we were talking about the particle in a box in one dimension. Namely, psi of r equals a has to equal 0, or u of a has to equal 0, put in terms of u. So our boundary conditions are relatively simple. The equation we have looks complicated and will end up having rather complicated solutions, but is at least straightforward to write down. And outside, of course, everything is easy. So, just as a basic case, what happens if L equals 0? L now is a separation constant we got from our spherical harmonics, so there is some freedom there. We may end up with solutions with L equals 0. What might those solutions look like? Well, if L is 0, our centrifugal term vanishes, and when our centrifugal term vanishes, we're just left with this for our radial equation. And if you look at equations like this, you should guess, well, I'm going to have something to do with exponentials because I have a minus sign here. Maybe I've got complex exponentials. But in this case, it turns out to actually be simpler to write u of r is a sine kr plus b cosine kr. That's reasonably straightforward. You can see plugging this into taking the second derivative, you're going to get out at minus k squared, and you're going to get your same solution back. Everything works out. So this is fine. This, though, is our solution for u. It's not our solution for r. Capital R, our actual radial part of our wave function, is going to be u divided by r, if you remember the definition of u. So I'm going to have a sine kr plus b cosine kr divided by r for the radial part of my equation. This is slightly problematic if you look at it. If I have some cosine part here, meaning this constant b, which up to now has been arbitrary, if I have some non-zero value for b, I end up with something that looks like the cosine of r divided by r. As r goes to 0, the cosine of r is going to go to a constant, it's going to go to 1, so I'll end up with a divergence, a 1 over r sort of divergence. That doesn't necessarily cause problems in general for wave functions in spherical coordinates, but in this case, since our potential is so simple, there's effectively nothing special about the position at the center of this sphere. If we displaced very slightly from the center, the wave function wouldn't change. You could just as easily express the sort of functions that you would get. Thinking about things physically, if you were in the center of a very large spherical room, it would be difficult to determine whether you were actually at the center. So it's unlikely that the wave function diverges, that there's anything mathematically special about the wave function. So the fact that this blows up as r goes to 0 implies b is equal to 0. We don't want to have any divergence at the center, since nothing special happens to our potential at the center. If you want to think about your wave function just conceptually here, as a function of r, it blows up. It would blow up as r goes to 0 if b was not equal to 0. Thinking about that in sort of two-dimensional space, for instance, if we're looking at a slice through the center, we would have a wave function that blew up at the center. Blowing up the center means you have sort of an infinitely sharp peak here, and that infinitely sharp peak would cause problems if you think back to our discussion of the momentum operator. We would have at least a discontinuity in the first derivative of the wave function as you pass through the point, and that would be associated with non-computable or infinite or whatever values of the momentum at the center. So since we want well-behaved solutions, we can't have any non-zero value for b. This is kind of a subtle point. Hopefully I didn't talk about it too much. At any rate, our wave function now, if L is going to be equal to 0, our wave function psi of r, theta, and phi is going to be some normalization constant times just sine of kr over r, and then we're going to multiply it by the spherical harmonic y, 0, 0 of theta and phi. But y, 0, 0 of theta and phi is relatively simple. It's just a constant. So actually, our wave function here is just going to be sine kr over r. Give me a moment to move things out of the way here. What this means is that this is the form of our wave function. We haven't yet specified anything about the value for k here, and as when we were discussing the particle in a box in one dimension, the boundary conditions are what fix a value for k, and what enforces quantization of the energies, of the allowed energies for the system. So if you think about the boundary conditions now, u of a equals 0, what that means, the only way that this part here, sine kr over r, can ever be 0 at r equals a is if sine of k times a is equal to 0. This is very similar to the analysis we did when we were talking about the particle in a box. This means Ka is going to be equal to some integer times pi. And here is an element of the integers. And if you plug back in for the definition of K, you end up with exactly the same expression we had before, that the energy of this is going to be n squared pi squared h bar squared over 2m a squared. And I'll put this in a box, but it's really only true for L equals 0 here, and that's important. This is not a general expression for the allowed energies of the particle in the infinite spherical well, but it is an expression for L equals 0. We get the same sort of structure as before. So what do we get for L not equal 0? If L is not going to be equal to 0, the actual equation we have to solve is the same equation we were talking about before. And unfortunately, this equation is difficult to solve. Really, in order to solve this, you have to go and talk to an applied mathematician. And the applied mathematician will identify this for you as the Spherical Bessel equation. This differential equation has a name, and the general solutions, he would be happy to write down for you, are given in terms of what are called spherical Bessel functions and spherical Neumann functions. J sub L of kr plus b times r times n sub L of kr, where J sub L are called spherical Bessel functions, and n sub L are spherical Neumann functions. So those are special functions, much like sines and cosines. You can go and talk to applied mathematicians and you can learn all about the properties. There are orthogonality relationships, there are normalization conditions, there are integral formulas, there are derivative formulas, there are series expansions and asymptotic forms. There is a lot of mathematics that goes into this. But for our purposes, since it is useful to be able to calculate these things, the simplest way of writing them down is that J sub L, the spherical Bessel function, just treated as a function of some variable x, you can think of as defined as minus x to the L, 1 over x to the L, times the nth derivative with respect to x of sine of x over x. Likewise, the spherical Neumann function can be defined similarly, minus x raised to the L, 1 over x to the L, times the nth derivative with respect to x of the function cosine x over x. So the connection to sine and cosine is still reasonably clear. But yes, these are just special functions, and if you want to make some calculations with them, you can probably do it. There is a lot of mathematics that will assist you in those calculations. But there's no simple way of writing down a formula, just like there's no simple way of writing down a formula for, say, sine of x. This is our general function, or our general solution to the spherical Bessel equation, which is what we got by doing separation of variables. This cosine x over x in the Neumann equation, the spherical Neumann functions, also poses problems. N sub L of x blows up as x goes to 0. So what this means is that, again, in our general solution here, we have to have b is equal to 0 in order to impose some physical sensibility on our solution. We weren't allowed to have a cosine term if L equals 0. We aren't allowed to have a Neumann term if L is greater than or equal to 0, for that matter. So how do you actually do math with these things? Well, one way to do it is to go and look it up in Abramowitz and Stegun. Abramowitz and Stegun is one of the canonical reference guides that you see physicists cite all the time. Nowadays, people don't actually use books like this because we have computers, but this is, for instance, is a table of common logarithms. No one really uses logs anymore, but there are more than 1,000 pages of useful formulas, integrals, derivatives, all of that nice mathematics. Or you can pull it up in your computer algebra software and make some plots. This is a plot of what the spherical Bessel functions actually look like. So this is related to our radial part of our solution. Sorry, this is our radial solutions. The red curve here, this is for L equals 0. We're looking at J sub L of x now. So this is L of 0, this is L equals 1, L equals 2, L equals 3, L equals 4, etc. as shown in blue. So as L increases, this thing sort of gets smooshed down near the center, which makes sense because as L increases, the centrifugal term becomes larger and larger, and the particle is therefore less and less likely to be found near the center, since doing so would require the particle to have more and more and more energy, essentially. One thing to notice is these are oscillatory functions. J sub L here for L equals 0 was our solution that we got when we gave L equals 0. So here, J sub 0 of x is just sine x over x, or is proportional to it. In fact, there will be a normalization constant here, of course, since we're dealing with wave functions in quantum mechanics. But sine x over x is going to have zeros at pi and 2 pi and 3 pi and 4 pi, etc. J sub 1 here also has somewhat periodic zeros. They're not as periodic, unfortunately. And that's what we need if we're going to figure out how our boundary conditions work. When we just had sine x over x, it was easy to tell where x was equal to 0, and we could tune the other associated constants, namely the energy of our wave function, the energy of our state, such that the constant multiplying here, x for instance equals to k times r, we could tune this k, we could tune the energy, such that we had a 0 at the outer wall of our spherical well. Knowing exactly where those zeros are, we know exactly what those energies should be. And unfortunately, the zeros for the higher order spherical Bessel functions are slightly harder to find. You really have to do them numerically. There's no closed form expression for instance, the 6th zero of J sub 4. So we make up some notation for that. I'm going to call beta n sub L is going to be the nth zero of J sub L. So for instance, this point here is going to be the first zero of J sub 1. And you can look up the values of these beta sub NLs in Abramowitz and Stegun. It's in chapter 10, according to Griffiths. So our boundary conditions look much the same as they did before. We just have to express them in terms of these unknown zeros. So again, U of A has to be 0, which implies that J sub L of Ka has to be equal to 0, which implies instead of Ka being equal to n pi, Ka has to be equal to beta sub nl. Depends on two things now, not just n, it depends also on L, where this beta sub nl is the nth zero of J sub L. If you make the same sort of expansion as before, you end up with the energy of our state in this context being h bar squared over 2ma squared times beta sub nl squared. So that tells you what the energy of a general solution to this spherical well potential. It tells you what the energy is if you know what the zeros of the appropriate spherical Bessel function will be. So our actual solution in the end depends on three things. It depends on n, the index of the zero that we're looking at. It depends on L, the separation constant in the separation of variables that gave us the spherical harmonics, the angular part, and depends on m, the constant that arose from the solution of the phi equation. and it's going to be a function of r, theta, and phi. And it's going to be given by, of course, a normalization constant out front, j sub l, of beta nl r over a, multiplied by our spherical harmonic, ylm of theta and phi. So this is our fully general solution, and it depends on n, where n is an integer. L, I'll just say L is going to be 0, 1, 2. It's a positive integer. And m, which is anything between minus L up to L. So we have these three integers that we need to choose in order to uniquely identify a particular stationary state solution to the Schrodinger equation in all three dimensions. So that's how these things end up working. Solutions in higher dimensions like this, in 3 dimensions, often end up involving these special functions, in this case the spherical Bessel functions. Occasionally you can make arguments on the basis of continuity or on the basis of well-behavedness of your special functions that you can throw out certain subclasses of your solutions. But what you'll end up with is going to be indexed by some integers if we have a quantized solution, or some continuous variables, for instance the momentum of the state, if we had something that was not fully quantized. For instance, our free particle in 1 dimension. You can do a free particle in 3 dimensions just as easily. These are your stationary state solutions then, and as before, you can add your time dependence back in. You're going to get something like e to the minus iet over h bar, as before. And you end up with your full solution. The time evolution of an arbitrary initial condition can be expressed then as this in the same sort of way, using your Fourier's trick, using the orthogonality now of spherical Bessel functions and the orthogonality of spherical harmonics. You can express your initial conditions in terms of your stationary state solutions, add the time dependence on, and you have your answer. That's how these problems are typically solved. To check your understanding, here are a few basic questions just asking you to determine the structure of the solutions. What are the allowed values of the constants that we got here? And how many zeros are we actually working with in a particular case? How many values of r between 0 and a is this particular spherical Bessel function evaluated using these betas going to equal 0?